Okay, so we are in Statistical Rethinking, second edition, and we're on chapter 12, and we're on the last medium difficult question, 12M3. Okay, so we want to modify the derivation of the zero-inflated Poisson distribution from the chapter to construct a zero-inflated binomial distribution. Okay, so that's what we're going to do. But let's just quickly recap the zero-inflated Poisson distribution. Okay, so we might, how do I want to say this? In the chapter, this was conceptualized as following. Okay, so we have a count variable, and in the book, it's the number of manuscripts, a school of monks are producing each day, right? So in a given day, they might produce 0, 1, 2, 3, 4, so on. But the monks are not simply, each day may be subject to one of two types of schedules for the monks. Either they have a typical work day, okay, in which case, the distribution of manuscripts they produce is distributed as a Poisson variable, or they take the day off and drink, and they're too drunk to work. And in those cases, the distribution is always y equals 0. Okay, and so this leads to a situation where the value of y equals 0 has more than one way of materializing, right? Either the monks work, but for whatever reasons that they just did not produce a manuscript, or they don't work at all, in which case, of course, no manuscripts are going to be produced, right? And so because of that, there are more zeros in the distribution than we would expect from a Poisson distribution. Okay, so that's the idea of the zero-inflated Poisson distribution here. Okay, and so this got conceptualized very well in this image, figure 12.3 from the book, right? Where we have the two types of days, work or drink, and that is distributed as a Bernoulli random variable, where the probability of drinking is p and of not drinking and therefore working is 1 minus p. And then from each of those, we go on to the respective probability distributions, right? Where if we're coming out of work, it's a Poisson distribution that may have 0 or not 0. Or for drinking, it's really not even a distribution. It's deterministically 1, or I'm sorry, deterministically 0 manuscripts. Okay. So we could formalize this process into a probability distribution. Okay. And so I've done that here over 2 lines. Okay. So we have that the probability that y equals 0, given the Bernoulli random variable parameter p and the Poisson lambda parameter, would be this, right? So we could go down the p path. Okay. So we produce zeros. Oh, we produce zeros. Sorry. How do I do that? Okay. We produce zeros p% of the time because of this process. But if we go down the other process, 1 minus p, where we're actually working, well, now we're in the Poisson domain, and our probability of producing 0 in the Poisson domain is this right here. Okay, so this is that's the Poisson distribution for 0 manuscripts produced. It's just e to the negative lambda. If you want to see how to derive that, this is the Poisson probability distribution, right? And so if y equals 0, then we have lambda to 0, so that just makes 1. And so then the numerator just becomes e to the negative lambda. And then oh Lord. And y factorial here, if y is 0, 0 factorial is 1, right? So we're just left with this right here, okay? So now the probability that y of, so now if y is not 0, so y given y is not 0 in the other 2 parameters, okay? Well, now we go down this path, right? So if we go down the p path, we never produce y greater than 0. So this is effectively 0, okay? So we can ignore this path right here. So we have 1 minus p, okay? And then how many manuscripts do we produce that's greater than 0? Well, then it's the Poisson distribution, right? So we went down this path and then this path, okay? And so we get this probability distribution, Okay, so our probability distribution for the entire process then is distributed over these two lines. All right, so now what we want to do is, instead of working with a Poisson distribution, we want to work with a binomial distribution down here, right? So if we go to work, now we're talking about binomial distributions, okay? And we want a zero-inflated one. So all we need to do really is replace the Poisson parts in this first part that we went over with binomial parts. And now remember that the binomial distribution looks like this. Oops. Well, has this right here, the n choose y here, okay? And so because we're already using p for the Bernoulli, I'm going to say that the probability of success of, of however many, of a success of a manuscript being produced, I'm going to call that q in the binomial distribution here, okay? So we can go down the same path here. So let's first look at the probability of producing 0 manuscripts in a binomial type distribution, okay? So I could go down p, okay? So I have p, right? And then to that, I need to add this branch here. So 1 minus p% of the time, I am, in binomial land, so not Bernoulli, but binomial land, okay? And what's the probability of producing 0 here? Of producing 0 manuscripts? Well, it's 1 minus the probability of producing any manuscripts over however many trials, right? So this is, probability of failure n times, okay? And the only way that we can produce y equals 0 is for all n trials to be 0, right? So this would be our probability distribution for y equals 0, right? And now if I want y to not equal 0, greater than 0, okay, well now this path is irrelevant to me, right? The p is not there because I know that y has to be greater than 0, so this p does not make sense to have in the equation. It's just being multiplied by 0, okay? So I go down the 1 minus p pathway, okay? And once I'm down the 1 minus p pathway, now I am just a binomial random variable with y successes, okay? So it's 1 minus p times the binomial distribution for, y successes, okay? And so that does it.